Hey there, welcome back to 2241. Today we're going to talk about multivariable functions and start our new chapter on partial derivatives. Okay, so let's go over our terms. We have to cover 2, 3, and multivariable functions. Multivariable is general for any number. It could be 5, 15, 136. We'll cover independent and dependent variables. We'll cover the graph of a function. That'll be used once in a while. Linear functions of the vector x now. Level curves, surfaces, and sets. And we'll see what those are later. A half space, limits of multivariable functions, what it means for them to be continuous, and polynomial and rational functions of a vector. All right, so next up we have our formulas. Our functions will be denoted in these ways. So we have functions of one variable with a single input x, functions of two variables with two inputs, x and y usually. Three variables will usually have x, y, and z, and n variables will usually have either indexed variables x1 to xn, or just a vector variable as sort of a catch-all for all of this. The other one that sometimes shows up is four variables. This doesn't get used too much, but it's good to know. I didn't write it down, so we'll write that down. So mathematicians are weird and they like to put W after Z. But for four variables, this is what we usually write. All right, so next we have the domain, and I've written some of these in more mathematical notation, and I'll explain how this is supposed to be read. The domain of a function in 1, 2, 3, 4, or 5, or 17 variables or whatever is the set of all inputs. So this is for a function of two variables. Inputs, which are ordered pairs, x, y, in R2, so that there exists an element z of R, the real numbers, where z is equal to f of x comma y. It's the output of applying f, the function, to the inputs x and y. And maybe I'll write that down. So this is the set So this is the set of all ordered pairs x comma y such that x comma y in R2 such that there exists, that's what this symbol right here means, a real number z such that z is an output of f. So you take f and you apply it to this ordered pair xy and you get out z. And xy is the solution to this equation. Okay, so that's what that is supposed to be read like. Similarly, we have the graph of f, which I've written in two different ways here, but they're supposed to be considered to be the same, just slightly different formalisms. So we have the set of all ordered pairs where the first input is itself an ordered pair, and the second coordinate. The first coordinate and the second coordinate. The first coordinate is an ordered pair, the second coordinate is a single real number. And so I've written that as R2 cross R. And then such that z equals f of xy. So same thing, but now I'm specifically including what that z is in the graph of f instead of just the domain. So the domain only counts the inputs, the graph counts the inputs and the outputs. The other way that we can do this is just ignore the fact that this is an ordered pair, and that'll be something that we just know. And so we have the ordered triples here, x, y, z in R3, satisfying this equation, z equal f of xy. And that's the graph of f. And you can think of this as just a formal way of saying, here's the surface consisting of all points x, y, z, satisfying this equation. It's literally the graph like you would put in the xy plane. All right, so what else do we have? Linear functions. What do linear functions look like in multiple variables? Well, we've actually already seen one of them, the equation of a plane. And so that's what this looks like. So this is supposed to be thought of as like a z. Then we have ax plus by plus k. Doesn't really look like a k, does it? That certainly doesn't look like a k. But ax plus by plus k. And then another way to write that is as the dot product of these two vectors. We've seen this before. And so this is the equation of a plane. That's a linear function in 2 variables. In 3 variables, we have ax plus by plus cz plus k equals w. So you can think of this guy as a w now. Again, that's also a dot product plus some constant. And this would be the equation of a hyperplane, or a 3-dimensional space in a 4-dimensional space. And then for n variables as an input, we have the same sort of thing. We just sort of extend out the number of things being summed up here. And we can write that more generally as constant vector times our variable vector x plus another real number k. And that should be equal to our variable vector y over here. Okay, and this is a n-dimensional hyperplane, whereas this was a 3-dimensional hyperplane, 2-dimensional. This is an n-dimensional. All right, level sets. Okay, these are fairly straightforward. They're the set of all inputs in the domain so that f is constant for a fixed k. So you fix k, there's a parameter here for this set, and it says, all right, if you fix k, then you get one set. And it's all of the xy so that f of xy equals k. We'll see some more examples of this in the examples video. All right, what about limits of multivariable functions? All right, so these are a little bit wordier, and I'll walk you through these. So the limit of a multivariable function, in 2 variables in this case, looks like this. So I say L is the limit as x comma y approaches a comma b. So we have a notion of distance in the xy plane. Things can be closer or further apart. So the limit of f of xy as xy approaches ab. If f of xy, the output, can be made as close to L as we would like by making x comma y sufficiently close to AB. So I can control how I can control the error sufficiently in the output by sufficiently controlling the error in the input. That's all that limits are talking about. And L is just the value that we are controlling the error with respect to. And so here's a mathematical restatement of that. So it says for all epsilon greater than 0. This is for all there is a delta greater than 0, such that for all x and y in the real numbers, whenever, so this is an if-then implication, whenever the norm of xy minus ab, think of these as vectors, is less than delta, then the absolute value, the norm in 1 dimension of fxy minus L is less than epsilon. So you control this error, you control this error. Whenever you control this error, you get to control that error as well. That's all it's saying. All right. Now, in 2 dimensions, we have a little bit more freedom to compute limits. It says the limit along a path now. So in 1 dimension, we only had from the left and from the right to approach a limiting value. In 2 dimensions, we have along the positive x-axis, along the negative x-axis, along the positive y-axis, along the negative y-axis, along a curve getting closer to the point, along a curve spiraling around the point maybe, along a straight line coming into the point at a different angle. There are all sorts of different ways to limit towards a specific input value. And different ones can give us different output values for certain functions. And that would be bad because that means that our limit doesn't exist, but that is something that we have to contend with here. So typically we'll have our functions parameterized in some way, x as some capital X of t and y as some capital Y of t function. And we say, all right, the limit as xy goes to ab of f of xy is equal to the limit as t goes to some parameter c of f of the parameterized functions if these limits exist and are equal for all paths xt, yt. Now, all paths, that's a pretty big quantification there. There's a lot of paths that we can use. It could be an ellipse, it could be a spiral, it could be linear functions, quadratic functions that we can approach along. So this is a pretty big, strict requirement here. This is a little bit more general because it covers every possible direction all at once, but it's harder to write down formally, or to write down when you're actually doing these. Okay. So typically we will use limits along paths to show that limits do not exist. All right. We also have a squeeze theorem in 2 dimensions. That doesn't change. So if g of xy is less than f of xy is less than h of xy for all xy close to ab, and the limits of the lower bound and upper bound at ab are the same, assuming both of these exist, then the limit of f of xy near or at ab exists and is also equal to those two. So you get to squeeze the limit of this guy in between the limits of g and h. Next up, we have continuity. What does it mean to be continuous in 2 dimensions? Same thing it means to be continuous in 3 dimensions. It means that you can pass limits through the function. But it basically means, all right, here, if I do the limit definition and instead of L, I write f of ab, then f is a continuous function. So let's read this through. F from R2 into R is continuous. That's my abbreviation, CTS. At AB, if the limit as xy approaches ab of f of xy is equal to f of the limit of xy as xy approaches ab. Well, that's pretty easy to compute. It's just ab. And this right here, this is what it means to be continuous, is that f and the limit get to swap order. So you can do the limit before computing f, and that is what makes a function continuous. So in other words, f is continuous in general if it is continuous at all points in its domain. Last, polynomials in xy. We know what polynomials look like in general for 1 dimension. So they have some coefficients and powers of x. Now we have powers of x and y and combinations of the two that we have to worry about. So there's a slightly different way of organizing these. We need doubly indexed coefficients here. So there's the constant coefficient 0, 0. And then the first coefficient is going to record the power of x, and the second coefficient, the power of y. So here we've got x to the 1 power, y to the 0 power, x to the 0 power, y to the 1 power. Here we have x squared and y to the 0, x and y both to the 1 power, y squared and x to the 0 power. And over here, this is our last term, x to the m, y to the n for some m and n values. And I like to sometimes organize polynomials into a matrix for two variables. For one variable, you can think of just like the row of a matrix or a sequence. For three variables, you have what's called a tensor, which is like a big three-dimensional, four-dimensional, whatever matrix of coefficients. But this is just a very convenient way of organizing these things together. And so this is a polynomial function in two variables now. We also have rational functions in x, y. These are quotients of polynomials. And these can also be written in sort of a matrix form, but it would have to be a pair of matrices. So you have the upper matrix and the lower matrix of coefficients. These two things have to be polynomials to give this a rational function name. All right, so those are all of our terms. And next up, we have our objectives to cover. First off, I want you to just understand everything that's in this section. So there's a lot going on, and it is important to know what all of the terms mean, to know what's being referred to in different problems. So make sure that you read through all of those and you're very familiar with all of the things that we just talked about, or at least the names of them. I want you to know how to compute domains and ranges. This is an important skill to have later on when we need to do things like think about the types of objects that we're dealing with and where things are getting plugged in. The other thing is that you should be able to compute, interpret, and graph level curves. So you haven't seen these too much yet, but it's not really that difficult. You just have to get used to turning three-dimensional things into two-dimensional things. Once we've done some examples, this should become an easy objective. All right, medium. I want you to be able to graph domains, asymptotes, and functions, or at least understand visually what they should look like. You should understand the idea of the limit for multivariable functions. This is actually kind of important. You should know the difference between when we're showing that a limit is not or does not exist and showing that a limit does exist, because they're sort of very different ways of computing things. Last, for mediums, we want to be able to compute limits and check continuity with the various techniques. Okay. Now, the hard goals are to understand the formal conception of the limit with those epsilons and deltas. That was that mathematical statement that I wrote down. And last, be able to understand and analyze the graph of f given its algebraic form. So a lot of functions that we might see can be very difficult to understand if you just look at them as one piece. But if you're able to break them down into different pieces, then it makes a little bit more sense to understand them in those small pieces. All right, so let's go over our terms a little bit more in depth here. So 2, 3, and multivariable functions, we always like to have a picture along with these sorts of things. So for two variable functions, we have our xy plane, and f takes points in this xy plane, and they get pushed through this arrow into some place on the z-axis over here. And so f is the function that's doing that. Our three-dimensional functions, three variable functions here, take a point in 3D space, and they push this through the function f and get out another value on the w-axis now. So this is a completely separate axis, and now you can see why we can't really graph the surface f in or when it has three variables, because we already used those three variables as inputs, and I don't know how to do things in four variables. It'd be very convenient if I did. All right, and so last, when we have n variables, we kind of just give up and draw blobs. You can think, all right, maybe we have like 5 variables here, and so 5 different axes. They're all supposed to be at right angles to each other. this is just impossible to draw in 3 dimensions. And so we typically just draw like a big blob and maybe draw a couple of axes here and there to give us the idea. And then we have a point, and that gets mapped through the function f to some number y over here. So those are multivariable functions. Next is the independent variables and dependent variables. So this is sort of a matter of perspective, because lots of functions can be thought of as functions of certain variables, and you can flip them around and make them functions of the other 2 variables, and so. So in z equal f of xy, I'm thinking of z as the output, so it's the dependent variable, and xy as the inputs, so they're the independent variables. You can think input, independent. And f itself is the function. It's the thing that's turning xy into z. Okay, so here are our dependent variables, and that's backwards. These are supposed to be the independent variables. So the independent variables are on the left side with the inputs, and the dependent variables are the outputs. And the function itself is this arrow. All right, what is the graph of a function? Well, it's exactly what you think the graph should be, but this is what it looks like in 2 dimensions. You have a whole surface here, because you have a surface of x, y values to plug in, and for each one of them you get out a z value, and this function is continuous, so everything kind of smoothly meshes together into this big surface. Graph of f is the set of all pairs I comma o, where I is an input and o is an output for f. So I in the domain, o in the range of f. All right, what do linear functions look like? It's the equation of a plane in slope-intercept form. So z equal ax plus by plus k. All right, if x equals 0, so along this plane, the yz plane, then z equal by plus k, that's this line. If y equals 0, we get z equal ax plus k. So y equals 0, we get the xz plane and this line. And then if z equals 0, we get ax plus by equals plus k equals 0. And so that's this line right here. And those 3 things make a triangle. Triangles contain vectors that are coplanar, and so we can make a plane with all of those things. So that's why a linear function of some variable is the equation of a plane. So let's come up here and look at the half space. So the half space is literally just half of all of space here. So we have x, y, z axes, and I'm saying, all right, cut things in half along the xz plane, and then take all of the things to the left, or maybe all of the things to the right. Here we have everything to the left, and so I have h, y, so all of the x, y, z triples, where y is less than or equal to 0. I could make this less than 0, and then this would be sort of a dotted plane. Sometimes, like how when you have inequalities, you draw dotted lines for those. But that would be like an open half space. This is a closed half space. And in general, you pick a variable xi, and you say, all right, I want that variable to be less than or equal to 0, or maybe less than or greater than or equal to 0. You can also choose less than or equal to some other number here, and that would give you a different half space. The other thing that you can do is you can have half spaces at weird orientations. So you pick a plane, pi, with some variable or some normal vector n and some displacement k from the origin. And then you take this plane and you say, all right, well, the half space below or above the plane is everything less than or greater than 2k, according to the dot product here. So those are half spaces. They can be useful to know about. The limit of a multivariable function. Here's a picture of what this can look like. So if I look at L1, this is the limit along the path where x is 0. So I come in along this axis, and everything is 0, I come towards the z value here, that's 0 in the limit. Whereas if I look at L2, I'm coming in along the path where y is equal to 0 and x is positive. And so I come towards the z-axis along this path, and now my limiting value is something a little bit larger. Maybe this is like a third or something. And so these two limits are not equal to each other, and therefore we have to say that the limit as xy approaches 0 of this function does not exist. So there is no limit at 0, 0 of this corkscrew-looking function. The other thing is if we come in along the negative axis, negative y-axis here, then I'm coming in up here. So even coming along the positive and negative axes, we get different values. Continuity is when that doesn't happen, when you get limits from all directions at every point are equal. And so we use sort of coming in along a circle to sort of grab every possible path all at once. When the values of f are close to the values of fab, whenever x is close to ab. Okay, so I don't get any weird jumps, or I don't get anything. There's like lots of oscillation near the point. That doesn't happen. And so we have a continuous function, f here. Polynomial and rational functions, what are some examples of these? Well, we've seen quadric surfaces. These are degree 2 polynomials in x, y, and z. Cubic surfaces. These are a little bit more complicated, but you have like x cubes in them. Asymptotes and singularities can occur across entire curves. So this is a little bit more unique for multivariable polynomials and rational functions. And let's take a look. So here's one example of a rational function. This one has no zeros, but it does have an asymptote. And if you take this function here, 4 minus 2x squared minus y squared, well, that is, if that's equal to 0, 4 minus 2x squared minus y squared, then we have the equation 2x squared plus y squared equals 4. Divide by 4 and you get x squared over 2 plus y squared over 4 equals 1. And I actually have this backwards, don't I? That's fine. But you get an ellipse shape here. And this, remember, was where the denominator was equal to 0. So this whole ellipse is an asymptote, a set of asymptotes for the function in blue here. And so on the outside, it turns out this function is negative and it goes down towards the asymptote. And on the inside, the function is positive and it goes up towards the asymptote. You can do that, or you can figure that out just by checking some values. So if I put 0 in here, I get 1/4, which would be at the bottom here. And that's a positive number. And then if x and y increase, then I'm subtracting a little bit from 4. And getting the bottom closer to 0, which means that I'm taking 1 over a small number and I get a very large number. Whereas on the outside, okay, now I've started subtracting very, very large numbers from 4, and now I just get negative numbers out. Okay. So those are polynomial and rational functions of x. Finally, we'll talk about our level curves. Level curves. So these are the sets of points where f is constant in the domain. And these are sort of like topographical lines. If you've ever seen a topographical map, like if you're going hiking or for some sort of environmental application, maybe you went to a national park, you've seen things that sort of look like this. So f, the graph, has a surface sort of shape here. It's in 3 dimensions, but along certain paths, the z value is constant, it's fixed. And so maybe here it's 0, here it's 1, 2, 3, and 4. And then over here, we can think, all right, well, if I'm looking down from above and I just draw those lines in the xy plane, then I get a map like this. And I can label them label each of those lines with the height of that line. So now I have a two-dimensional representation of a three-dimensional object. And it's sort of a way of compressing information for us to look at things a little bit more easily in 2 dimensions. Okay, so those are all of our terms. We've seen lots of nice pictures, and we've got our formulas under our belt now. We'll come back in the next video and start doing some more examples of computation with multivariable functions.